Hello, welcome to Quicker Calc. I make these videos for the AP Calc AB/BC curriculum, but they can also be applied to any college level calculus course. Today I'll be explaining derivatives, what a derivative means, and how to take one. Let's say we have this chart of data points. These points describe a small dog's position from 0 to 2 seconds, like a small evil dog. So at 0 seconds, the dog is at 3 feet from a starting position of 0. At 1 second, the dog is at 5 feet from that 0 position. And at 2 seconds, the dog is 9 feet. Maybe you've noticed that the amount the dog's distance has increased per second has increased over time, as if he has someone to harass and there's a rate of change increasing the rate at which he runs, which causes the distance to increase more and more every second. Calculus is exploring and identifying these rates of change. You may remember from algebra that the slope of a line can be identified by change in y over change in x, and in doing so, we are finding the rate of change, also known as the derivative of a straight line function. Let's quickly look at the line f of x equals 2x plus 1. We can quickly plug in any 2 points and find a constant slope or a constant rate of change of 2. If we think about it in terms of feet and seconds, the equation describes distance always being traveled at 2 feet every second, so the speed, or a better word, velocity, would be equal to 2 feet per second. These units also make sense algebraically going back to the change in y over change in x. But what about when the rate of change is changing and the function is not straight, like in a tinier super evil dog function like this, where he has rabies and is all over the place? This won't work because with the slope formula, a straight line is being drawn, and when the slope changes at any given point, the straight line will not always be accurate. In fact, it could be insanely wrong given the function. If we wanted to approximate the slope at x equals 1 using points at x equals 0 and x equals 2, our slope would be miserable. Instead, we could refer to the slope of the tangent line, which is a parallel line we can draw at a point representative of the slope at that point. Drawing a tangent line at x equals 1 provides a far more accurate slope and is closer to what we actually do when taking a derivative using calculus. Going back to the original example, if we wanted to approximate the rate of change at 1 second, or wanted to find the velocity at x equals 1, you would treat x equals 1 as a sort of midpoint and use the closest surrounding data to find the slope so that the line drew with the slope formula goes evenly through 1. So using change in y over change in x gives you a slope, which in this context is a velocity of 3 feet per second. To find the actual derivative, we need an equation, so let's use the function f of x equals x squared plus x plus 3. Here's how we go about taking a derivative in the simplest way. d dx means take the derivative of a variable, which we know embodies change in a function, let's say x, to the power of n, is equal to n multiplied by x to the new power of n subtracted by 1. This looks kind of crazy, but once you see an example, it won't be as bad. When we differentiate a function like this, we can treat each part of the function being added or subtracted as its own. First, we will multiply x squared by 2, the original power, and then subtract 1 from the original power, giving us 2x. Then we will do the same for x to the power of 1. Multiply by 1 and take off a power. Anything to the power of 0 is equal to 1, so the derivative of x is 1. 3 is a constant and is an element of the function that has no impact on the slope or rate of change, so the derivative is 0. Let's look at the original function in the first derivative function. You also need to know the apostrophe in front of the second f just denotes that it is the derivative of the original function f. I'll be referring to this as f prime. If you don't quite understand conceptually how f got to f prime, think about the value of the tangent line for each slope at each point. At f of negative 2, the slope of the tangent line is negative 3, so f prime of negative 2 equals negative 3. The exact same thing applies to the slope of the tangent lines at x equals negative 1/2 and x equals 1. The derivative graph is made from the slope of the infinite amount of tangent lines that can be made from the original function. It's important to completely grasp the concept of position, velocity, and acceleration as well. If our dog is moving at an increasing or decreasing speed, then there is either a positive or negative acceleration. Since the velocity changes linearly, there's going to be a constant acceleration, and as a result, as velocity is always increasing, distance is going to increase exponentially as every second our dog is more ravenous and able to travel at a higher velocity per second. And a reminder that velocity is the derivative of position and the derivative of velocity is acceleration. Here's a few practice problems to run through and a step-by-step on how I got to the answers. All I ask is you attempt the problem first and then watch my step-by-step and explanation. First, you gotta remember that the derivative of position is velocity and the derivative of velocity is acceleration. Once we get the velocity equation, all we have to do is plug in 4 to get our answer, and remember that the velocity at that instant is in feet per second, so very, very fast fish. Take the derivative again and we arrive at a constant, so no matter what time it is, the rate at which velocity is increasing is always the same. Every second the velocity will increase another 6 feet per second. In calculus, we work a lot with exponents, including negative and fractional exponents, which are a little bit uncomfortable at first, but with practice will be simple. Setting the function as x to the power of negative 1/2 makes it much easier to apply the power rule. Multiply the original power of negative 1/2 and then subtract the original power by 1. The answer in exponential form is enough for the AP exam, but I thought I'd clean it up a little bit. And before the video ends, I want you to draw what you think the derivative of this graph looks like based on the slope of the tangent lines. Let's first start off with where the derivative is 0, which is going to be where the tangent line is horizontal. I'll dot these points on the other graph. Then, I'll look at the tangent slope at x equals 0, which looks to be about negative 1. Looking at the slope at negative 1, they seem to be both at about 2. And if I were to plot more and more points, it would end up looking like this. There are many kinds of functions that are not as easy to differentiate, but with a few rules, tricks, and practice, it won't be bad. So I'll be covering that in my next video. Thank you for watching, and I would be as happy as a fish swimming 32 feet per second if you could like, subscribe, and send the video to a friend who could use a refresher. Have a great day.